Einstein then introduced a complication that would shatter this simple picture. A passenger train raced past a platform at tremendous speed, carrying an observer who witnessed the same lightning strikes from a dramatically different reference frame. This passenger sat in the exact center of the train car, maintaining the same geometric relationship to the lightning strikes that Einstein held on the platform. The critical difference lay in motion. While Einstein remained stationary on the platform, the train passenger hurtled through space at enormous velocity. This motion fundamentally altered what the passenger would observe about the timing of the lightning strikes. The passenger would not witness the strikes as simultaneous events, even though both observers maintained identical positions relative to the lightning bolts. The light from the strike at the front of the train's direction would reach the passenger first. Since the train moved toward this lightning bolt, the distance that light needed to travel became shorter. Meanwhile, the light from the rear strike faced a longer journey because the train carried the passenger away from that flash. The moving observer would see one lightning bolt before the other, creating a clear sequence of events rather than simultaneity. This difference in observation created a devastating logical problem. The passenger would measure a specific time interval between seeing the two flashes. Einstein on the platform would measure zero time interval, seeing the flashes simultaneously. The same physical events produced different measurements depending on the observer's motion. Both observers were equally valid, equally positioned, and equally capable of making accurate measurements. The implications revealed that simultaneity depends entirely on the observer's reference frame. Events that appear simultaneous to one observer occur in sequence for another observer moving at different velocity. This relativity of simultaneity contradicted humanity's most basic assumptions about time. Simultaneity had always been considered absolute, a fundamental property of events that remained the same regardless of who observed them. The paradox created an impossible situation for traditional physics. If light speed remained constant as Maxwell's equations demanded, then simultaneity could not be absolute. If simultaneity was absolute as Newton's framework assumed, then light speed could not remain constant for all observers. The train passenger and platform observer could not both be correct about the timing of identical events using conventional physics. Modern particle accelerators provide real demonstrations of these effects with subatomic particles traveling at velocities approaching light speed. Scientists observe particles emitting light while racing through accelerator tunnels at tremendous velocities. These particles act as moving light sources, similar to Einstein's thought experiment, but with measurable quantifiable results. The emitted light maintains Maxwell's constant speed regardless of the particle's motion, confirming that light speed does not follow Newton's rules of relative velocity. Experiments at facilities like CERN create conditions where particles move fast enough for relativistic effects to become clearly observable. High-energy particle collisions generate debris that races away from collision points at different velocities. Scientists can measure the timing of light signals from these moving sources, testing whether simultaneity depends on the observer's reference frame. The results consistently confirm Einstein's predictions about the relativity of simultaneity. Quantum physics research has validated these observations at the subatomic level with unprecedented precision. Modern detectors can measure time intervals down to attoseconds, revealing how particle interactions that appear simultaneous from one reference frame occur in sequence from another. These measurements validate Einstein's insight that simultaneity depends entirely on the observer's motion through space. The Large Hadron Collider continues searching for any violations of these principles that might indicate preferred reference frames in spacetime. Scientists examine millions of particle collisions looking for evidence that certain directions in space might be special, which would restore absolute simultaneity. No such evidence has been found despite extraordinary measurement precision. Every experiment confirms that simultaneity remains relative to the observer's motion. Einstein's lightning strike thought experiment proved that Newton's relative motion and Maxwell's constant light speed could not both be correct under traditional assumptions about space and time. The train passenger and platform observer produced contradictory measurements of identical events. Their conflicting observations demanded a revolutionary solution that would challenge every physicist's understanding of reality. Einstein faced a choice that would force him to abandon fundamental principles that had governed physics for centuries, or discover something even more profound about the nature of time itself. Einstein faced an impossible choice between two pillars of physics. Newton's laws had explained planetary motion and mechanical systems for centuries, while Maxwell's equations had revealed the nature of light and unified electricity with magnetism. Choosing Newton meant accepting that light speed varied with motion, destroying electromagnetic theory. Choosing Maxwell meant accepting constant light speed, which would demolish the principle of relative velocities in cripple mechanics. Then Einstein conceived a revolutionary possibility that no one else had considered. What if both Newton and Maxwell were correct, but something else entirely needed to change? What if the conflict arose not from errors in their theories, but from wrong assumptions about the nature of space and time themselves? Perhaps reality operated according to rules far stranger than humans had ever imagined. Einstein proposed that time itself must be flexible rather than rigid. Instead of flowing at a constant rate throughout the universe, time could stretch and compress depending on motion and gravity. This elasticity would allow light to maintain its constant speed while preserving the principle of relative motion. Time would adjust its pace to ensure that light always traveled at 299,792,458 meters per second from every observer's perspective, regardless of their motion through space. This solution seemed completely absurd to every physicist of Einstein's generation. Time had always been considered the most fundamental constant in the universe. Newton described time as flowing uniformly everywhere, creating a universal rhythm that synchronized all events throughout space. Clocks might run fast or slow due to mechanical imperfections, but time itself remained steady and unchanging. The idea that time could vary seemed to violate the most basic assumptions about reality. Einstein's proposal challenged humanity's intuitions about existence. If time could slow down or speed up, then the ordered progression of cause and effect became relative to the observer. Events that appeared simultaneous from one perspective could occur in sequence from another. The universal timeline that connected all events throughout history would fragment into multiple timelines depending on motion and gravity. Reality would become far more complex and interconnected than anyone had suspected. GPS satellites provide daily proof that Einstein's solution actually governs reality. Each satellite carries atomic clocks that experience time dilation due to their orbital velocity of 17,500 miles per hour. Special relativity predicts these high-speed clocks should run slower than Earth-based clocks. Simultaneously, the weaker gravity at orbital altitude creates gravitational time dilation that makes the satellite clocks run faster. These competing effects produce a net time difference of approximately 38 microseconds per day. Without corrections for these relativistic effects, GPS positioning would become completely unreliable within hours. Errors would accumulate at rates exceeding 10 kilometers per day, making navigation impossible. Engineers solved this problem by adjusting the satellite clock frequencies before launch. The fundamental frequency of GPS atomic clocks is set to 10.229999543 MHz instead of the standard 10.23 MHz, creating an offset that compensates for relativistic time dilation effects. This frequency adjustment represents one of the most practical applications of Einstein's revolutionary insight. The offset factor of plus 4.465 times 10 to the power of negative 10 ensures that satellite clocks maintain synchronization with ground-based atomic standards despite experiencing different rates of time passage. GPS systems perform millions of these relativistic corrections every day, proving that time dilation is not just theoretical but essential for modern technology to function. The precision required for GPS accuracy demands nanosecond-level timing synchronization between satellites and ground stations. If relativistic effects were ignored, the accumulated timing errors would destroy the system's ability to determine positions accurately. This technological requirement validates Einstein's prediction that time must be flexible to maintain light speed as a universal constant. The Atomic Clock Ensemble in Space mission, launched in April 2025, tests gravitational time dilation with unprecedented accuracy by comparing atomic clocks on the International Space Station with identical clocks on Earth's surface. The ACES mission measures time variations across 10 sessions, each lasting 25 days, with precision down to 1 part in 10 to the power of 17. Einstein's breakthrough established the concept of time dilation as a measurable physical phenomenon. Time literally runs at different rates depending on velocity and gravitational field strength. Astronauts on the International Space Station age slightly slower than people on Earth's surface due to their high orbital speed. Mountain climbers experience slightly faster time passage than people at sea level due to weaker gravitational effects at higher altitudes. These differences are microscopic but real and measurable with modern instruments. The revolutionary concept that emerged from Einstein's impossible choice became known as special relativity. This theory unified space and time into a single four-dimensional framework called spacetime, where motion through space directly affects motion through time. The theory preserved both Newton's principle of relative motion and Maxwell's constant light speed by allowing time itself to be relative rather than absolute. Special relativity transformed physics by revealing that space and time were not separate, independent dimensions but components of a unified structure. The patent clerk who refused to choose between Newton and Maxwell had discovered that the universe operated on principles that would fundamentally reshape human understanding of reality
Einstein's
itself. Mathematical framework revealed exactly how this flexibility operated in practice. Time dilation followed precise equations that could predict exactly how much clocks would slow down based on velocity and gravitational field strength. The faster an object moved through space, the more dramatically time would stretch, causing clocks to run slower relative to stationary observers. This relationship wasn't random or approximate, but followed exact mathematical laws that governed the behavior of space-time itself. The International Space Station provides a perfect laboratory for observing this time elasticity in action. Astronauts aboard the ISS travel at approximately 17,500 miles per hour, experiencing measurable time dilation effects due to their high orbital velocity. Time passes slightly slower for these astronauts compared to people on Earth's surface. From their perspective, time flows normally, but precise atomic clocks reveal that they age at a different rate than Earth-bound observers. This effect demonstrates Einstein's prediction that motion through space directly affects the passage of time. The Atomic Clock Ensemble in Space mission, launched in April 2025, compares highly accurate atomic clocks aboard the ISS with identical clocks on Earth's surface. This mission measures gravitational time dilation with unprecedented precision by operating atomic clocks that were miniaturized from laboratory size to the size of a small refrigerator. The engineering achievement required to create these compact yet incredibly precise instruments represents a major breakthrough in space-based physics experiments. The ACES mission operates across 10 sessions, each lasting 25 days, and is controlled from the Columbus Control Center in Munich, Germany. These extended measurement periods allow scientists to accumulate data about time dilation effects over months of continuous operation. The mission's 30-month duration provides sufficient time to detect even the smallest variations in time passage between orbital and terrestrial environments. The measurements reveal exactly how much time stretches due to the combination of high velocity and reduced gravitational field strength at orbital altitude. Einstein's elastic time concept revolutionized physics by revealing that time deserved recognition as a fundamental dimension of reality. Rather than treating time as a universal constant that provided the backdrop for physical events, Einstein proposed that time was an active participant in the structure of the universe. Time could be affected by motion and gravity just like any other physical quantity. This insight elevated time from a mere measurement tool to a dynamic component of the cosmos itself. The revolutionary proposal that emerged from this understanding unified space and time into a single four-dimensional fabric called space-time. Instead of viewing space and time as separate independent dimensions, Einstein showed that they were intimately connected aspects of a unified structure. Motion through space created motion through time, linking the two dimensions in a mathematical relationship that could be precisely calculated. This space-time framework provided a complete description of how objects move through both spatial and temporal dimensions simultaneously. The space-time concept explained phenomena that Newton's absolute time and space could never account for. Gravitational effects, electromagnetic wave propagation, and high-velocity particle behavior all became comprehensible within the space-time framework. Scientists could predict how clocks would behave in different gravitational fields, how light would travel between moving objects, and how particles would interact at extreme velocities. The mathematical tools of space-time geometry provided solutions to problems that had puzzled physicists for decades. Mars missions illustrate the practical implications of elastic time for future space exploration. Astronauts on a 21-month journey to Mars would experience measurable time dilation effects due to their high velocity during transit. While the difference amounts to only a few nanoseconds compared to Earth observers, The effect demonstrates that time passage varies even for relatively modest space travel. Extended stays on Mars would create additional time dilation effects due to the planet's different gravitational field strength compared to Earth. The long-term implications become more significant for permanent Mars colonists. A human living 80 years on Mars would experience approximately 12 seconds less time than someone living exactly 80 years on Earth. This difference results from Mars having weaker gravity than Earth, causing time to pass slightly faster on the red planet's surface. While 12 seconds represents a tiny fraction of a human lifetime, it demonstrates that time passage varies throughout the solar system depending on local gravitational conditions. These measurements validate Einstein's insight that reality operates according to principles far stranger than common sense suggests. Time responds to motion and gravity like any other physical quantity. Clocks run at different rates depending on their velocity and location in gravitational fields. The universe maintains precise mathematical relationships between space, time, motion, and gravity that determine how physical processes unfold. The elastic nature of time means that simultaneity becomes relative to the observer's motion and gravitational environment. Events that appear simultaneous from one perspective can occur in sequence from another. The ordered progression of cause and effect varies depending on the observer's reference frame. This flexibility allows the universe to maintain consistent physical laws while accommodating the strange requirements of relativistic physics. Einstein's discovery that time could stretch and compress revealed that the space-time fabric itself was far more dynamic than humans had ever imagined. The rigid, mechanical universe that Newton described gave way to a cosmos where space and time formed a unified structure that could bend and warp.